All right, so we're going to be looking at radicals. Remember, radicals are what that underneath the square root sign. So we're going to look at those. This is a little bit, you'll start to see a pattern here with these exponents. But this gets a little bit tough because we're not very strong in knowing our perfect squares. So it really does help out to know all your perfect squares, and I'll write this down at the bottom of the page after we go through it. So look for a pattern here. So the square root of a to the 10th. When you take the square root of a perfect number, of a perfect square, let's just say 100. Remember that is really like the square root of 10 squared. Well, the square root of 100 is 10. Also, 10 squared is just 10. So take that and kind of sort of see that's like 10 squared. When you take the square root of it, you're really kind of taking out that squared part. So this really, remember when I multiply exponents, when I multiply the same base number with exponents, I add the exponents. So technically, I could write this as the square root of a squared times 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 the square root of a squared. So when you multiply all those, so you can kind of sort of take those and take those all out. When I find the square root of something squared, it's just that base number. So in here, it's just going to be a. So I have a times a times a times a times a. Remember, this is a to the first, or a times itself 5 times, which just looks like this, a to the 5th. So hopefully you can see that all I did was basically take this and divide it by 2, and you get your exponent here. That's what divides out, or I say divides. I guess it is a division part, divides out. So here for a to the 12th, the square root of a to the 12th is going to be a to the 6th. Then let's look at a to the 15th. So this is a little bit different. Because I have an odd number. But what's the closest number to that? That'd be like the square root of a to the 14th times the square root of a to the 1st, essentially. Well, a to the 14th, when you find the square root of that, you get a to the 7th times the square root of a. So just leave it like that with a radical sign in there. So when you simplify some of these, sometimes it's going to end up with a radical sign in there. You're just going to make everything else, if there's any kind of perfect square underneath the radical, you kind of pull that out by finding the square root of it. So looking at the same number with the square root of 23, or a to the 23rd power, you are going to get that'd be like the square root of a to the 22nd times the square root of a. So take 22, divide it by 2, and you get 11. So I have a to the 11th times the square root of a. So that's as simplified as it gets. Mathematicians don't like when you have a perfect square underneath a radical. They want you to pull that out. So that's kind of sort of something that you need to make sure that you understand, is that you don't want any kind of perfect square underneath the radical. So let's look at those perfects. So here, our pattern is divide exponent by 2. And the reason why you do that is because when you take the square root of something, so a to the 10th, the square root of that is really the same thing as a to the 10th raised to the 1/2 power. And if you remember, when you take a power to a power, you multiply. 10 times 1/2 is 5. So a to the 5th power. So that's kind of sort of why that is. So let's look at our perfect squares. I'm just going to go up. So I have 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. So that's 10 squared. 121 is 11 squared. So forth and so on. So you need to get a little bit, you want to be fairly familiar with these, probably up to 20. And they're pretty easy to memorize, but you can also look on your calculator, just do 13 squared just to see what it is real quick. All right, so let's look at these here. So we have 225 the square root of 225 raised to the 4th power. So the square root of 225 is 15. So I can take the square root of 225. So I could really write it like this, times the square root of x to the 4th. Well, x to the 4th is an even number, which makes it really nice and pretty. So therefore I have, that's going to be x squared, and the square root of 225 is 15. So 15x squared. It won't always be that nice and pretty, but for this time, you know it is. So this one, again, I would have the square root of 100 times the square root of x squared times the square root of y to the 10th. I just like breaking it up like this. It can all, once everything that's multiplied together can multiply together and go underneath the same radical, or you can split it up like this. It kind of works the same way. So the square root of 100 is 10, and then the square root of x squared is just x. Remember, you divide that exponent by 2. And then the square root of y to the 10th is y to the 5th. Remember, dividing it by 2. So 10x y to the 5th. That's what we have. So main thing is knowing your perfect squares. Here, this is where it gets a little bit So here I'm going to take this, divide it, the square root of 32 times the square root of a times the square root of b squared. So here we have 32. That's not a perfect square, but there is a perfect square inside of there. Actually, it is 16. So this really is like the square root of 16 times the square root of 2. And then this stays, so this kind of breaks up as this stays the square root of a, and then this I'll just keep as a square root of b squared, so now I can go through and take the square root of everything. So the square root of 16 is 4, times the square root of 2, times the square root of a, times b. Now notice that 4 and b are no longer underneath the square root sign, but that these two are. So I can put those back together underneath the same square root and keep my 4b out front and 2a underneath. Again, I don't know how much prettier necessarily to you this looks, but the fact that you can't find the square root of 2a is kind of why you want to leave that underneath the radical, and then you have 4b. Since you can find the square root of that, pull those out. Look at example 4 here. We have 25x to the 4th y to the 7th. So again, that's going to be the square root of 50 times the square root of x to the 4th times the square root of y to the 7th. Now, I can break this up as a square root of 25 and the square root of 2. It is very key that you know perfect squares. It's key that you know that this is 25 times 2. Don't do 5 times 10 because 5 and 10 are not perfect squares. So you want to find a perfect square that goes into that coefficient. I'm going to leave this as x to the 4th, and I'm going to leave this as y to the 7th square root of it. Okay, so now I can find my square root. So the square root of 25 is 5, and the square root of x to the 4th is x squared. I can go ahead and simplify that. That's going to be y to the 3rd square root of y. Remember, so I take this and it makes it like 6 and 1. So you take half of 6 and it makes a 3, and you keep the 1 here. So that's kind of sort of where those came from. All right. So now I can go put everything that's underneath the radical can go now together. So square root of 2y, and then everything that's outside of the radical can come out here. So 5x squared y to the 3rd times the square root of 2y. All right, looking at the 5th example here, notice that I have something out front here that I'll multiply by. So they're not underneath the radical at all. So I have a times b out here, times the square root of 75, times the square root of a, times the square root of b to the 4th. So remember that you're really looking at these as far as a 75 can be written as a perfect square. So a times b times the square root of 25 times the square root of 3. Don't use something else, because if you do, that's not going to work out, okay? Because it's not a perfect square. And then times the square root of a times the square root of b to the 4th. So I have, I can find the square root of 25, that's going to be 5, and the square root of b to the 4th is going to be b squared. There's nothing else These two stay underneath the radical. But I have all of this stuff to put outside the radical. So I have 5, make sure you write your coefficient first. So 5ab to the third, because I have a squared here and a b to the first here. But I don't have any other a's to get with it. Then I have the square root of 3a. That is the simplified form. And then lastly, I have negative 3x times the square root of 49 x to the x squared y to the 9th. So here, we're going to look and see, let's see, I have negative 3x stays out, and then times, negative 3 times x, I guess, times the square root of 49, times the square root of x squared, times the square root of y to the 9th. Now, this makes it really nice because this is a perfect square. The square root of 49 is perfect. It is 7. So I have negative 3 times x times 7 times x, because remember the square root of x squared is x, and then times y to the 4th square root of y. Remember again that you have this becomes basically 8 plus 1, and this is a and then once you take this and divide by 2, you get 4, and then you leave your 1 right here. So that's where the 4 and the 1 comes from. All right. So now we can multiply our numbers. Negative 3 times 7 makes negative 21. X times x becomes x squared. Then I have y to the 4th, and then square root of, looks like 4, y. So negative 21, x squared y to the 4th square root of y is what you want to leave that as. So simplify it all the way down as far as you possibly can. Pull out everything you can from the square root there. That was a little bit longer video, but this is a little bit tougher skill to master, mainly because you have to know the perfect squares. That's the key. Remember also that you're looking for odd and even exponents. And if it's odd, when you have one left over, that's what goes inside. So, those are kind of sort of your 2 rules that you're looking for. That is simplifying radicals.